Okay, last time we talked about the assumptions we made in order to make inferences for our simple linear regression model. If you still remember, the assumptions are linear, independent, normally distributed, and equivariance. So that's LINE. With these assumptions, we can make inferences like to do the intervals for our estimated slope, or to the prediction intervals and confidence intervals for predicted value, or for a regression line. And in this little example, I'm going to show you with this R code as how are we going to do that with this with coding. Okay, I picked the example on James' book, which is chapter 3. There's actually this is just a part of that example I'm showing you here. Yeah, let's just do it. I will post this R code online for you for your reference, and we'll also run it here. So this first library, we would have to attach it to our environment in order to use those functions inside this library. And also, before we can access the code, the data, we will have to install this package. If this is the first time you use this package, you just do this install.packages. Well, I actually have used it before. Let me see what it will show. Well, updating. No, actually, I have already. Well, ignore this. I think it just re-downloaded. But anyway, if it's the first time you use this package, you would have to install it. So this is the package come along with the book. It has all the data sets that will be used in the book. So let's attach this library. And the data set we're going to use is called Boston. Let's take a look at the data. So by put this question mark in front of this Boston, it will give you a nice help page on this data set, including all the variables, or do names. Boston, it will also show you all the variables, but they are all like abbreviated. They are short. It's hard to guess what they mean, so it's better to just look at this help doc. Like this crime is per capita crime rate by town. This chase is, it's Charles River, dummy variable equal to 1 if it's tracked bounds of river, 0 otherwise. So it gives you great explanation what it is. So this MED-V is the median value of all owner-occupied home in like this amount. This is the response variable we are going to use, and this LStat is lower status of the population, which is a percentage. Yeah, let's yeah, I did this attach this data set. In this way, you do not need to type like Boston $$ each time when you refer when you set a variable. Like here, I can directly do this MED-V and LStat to get the variable instead of doing Boston $$ MED-V. So without this attached, you would have to use this in order to set this variable. Okay, we got it attached. You can do this linear model fitting as we talked before. simple like this. So it just appear in your environment. It has all this information. And if you want to take a look, okay, by only like input this, it will tell you what is the coefficient and what is the the intercept, estimated intercept and the estimated slope for this linear model. And if we want to have more information, we do a summary of the model. So here it shows us this is the model you run and more detailed coefficients, estimates and the estimated standard error. And also it will give you a two-sided test, like both the intercept and the slope, to test if they are, if beta 0 or beta 1 equal to 0. So it gives you the p-value directly. So both are highly significant. And those 3 star being really close to 0, and 2 star, it just indicates the significance level. And it also shows you the R square. It shows you the RSE, the residual standard error, which we talked about at last week. This measures how good your model is, but mostly you compare this RSE among different models. So that's how you use it. And R square, it also gives you R square. You can see it has both this R squared and also this adjusted R squared. Well, this adjusted R squared is mostly used for multiple linear regression, where it would adjust for degree of freedom. So you have more than one, like many predictors, many X values, X variables. But for now, we can just focus on this for simple linear regression. Yeah, so this is the result from our linear model. Well, yeah, I put this names of this linear model. It shows you what are the variables that you can quote from this model. So for example, if you just want this coefficients, you can do either coef of this lm dot fit. When you do this, it gives you the coefficient estimates. You can also do this with a dollar sign to cite the variables. See, if you do this, it will give you the same thing. But like if you want other things, like if you want to get the residuals or fitted values, all different things, this is how you get them. For example, yeah, it has residuals, you can get the residuals in this way. Yeah, or you can also do anyways, this is another way how you get the residuals. It's the same as here. Just the reference, I'll put this here. Okay, and what about to get the confidence interval for this? This is the built-in function to get a confidence interval. Well, by default, it's a 95% confidence interval for both the intercept and the slope. So this is how you automatically get the confidence intervals. And how do you do the prediction intervals? And well, wait a second. So the first line here. Well, let me adjust this a bit so that you can see the whole line. So the first line, you see this argument interval being confidence. So the first line is doing a confidence interval for the regression line. and with you specified the new values to predict. And for prediction interval, this is how you do it. You just specify this interval being prediction, and it will give you the prediction interval, which is well, the first value is the fitted value, or the second and third column is giving you the lower bound and upper bound of the intervals. Again, prediction intervals are wider than confidence intervals because we have to quantify, we have to take account of this individual random errors. Well, if I want to do the plotting, get my data, and also add the regression line to it, this is how you do it. And of course, when you do the plot, you can always you can make custom plots by specifying what type of points, like those little circles by default. You can also do it like solid circles. This is solid points, and well, you can definitely choose. I'm just showing you how to do it. Oops, sorry. Oh. Yeah, so this is telling you how to choose. Like, I use the 16, which is this one, bigger solid dots. Well, you can choose, you can like just change the 16 to, let's see, or by default is 1, and you can do 2. It will give you circles. Oh, sorry, triangles, not circles. 1 is 2. The line for regression, and you can change the color. The color equal to 2, it's a bright one. And I'm just showing you how to customize your plots as you like. Well, I put a small, like this is another a small thing here. If we have, like I showed you this CHAS, what are they? It's a dummy variable, which is it's binary. And run this model. X equal to service plus 1, 2. So this is clearly very different from the previous plot, right? Because we have this response variable x being binary. See, it only has value 0 or 1, but you can still like do a regression on it. Or if you do this, add the line to it. It's like this. And by looking at its summary, it gives you an estimate for this slope. How do you interpret this slope? It's nothing but like when you change this CHAS from 0 to 1, how much it will lift your response variable, the y variable. So it's in a similar sense, but it's just the x variable. It's a bit different from before, but you can still run a linear model on it. Well, in the end, Don't forget to detach your data set. Otherwise, it might like mess up your environment when you run a different set of code. Some of the variables might have the same name. It can cause you trouble. So the good practice is you attach it when you use this variable a lot, and in the end, you always do the detach of this data set. Well, yeah, this is a short lab for previous week, just to refresh your memory of the knowledge that we learned.